In the previous time, we talked about process, variation, data, and statistical tools. Also, from their relationships, we discussed the concept of process improvement. In this time, I'm going to introduce one of the main statistical methods for process improvement called the statistical process control. Suppose that there are n observations generated or collected from a process of interest. These observations are the output of the process, and sometimes it is called the quality characteristic. Bold X is a vector with n values and represent a sample whose size is n. Since there exists inherent variability, those n values are not identical, even though they are collected from the same process. The simplest way to develop a model for observations having variance is to adopt a random variable and regard observations as its possible outcomes based on a probability distribution. The probability distribution specifies the probability of each possible values. Technically, we can express the model when the random variable xi follows a normal probability distribution in this way, where mu and sigma square represent the mean and variance of x respectively. There are three underlying assumptions on this model: univariate type of data, IID, and normality. First, the model considers only one variable for the output or one quality characteristic of the process. Second, we assume that collection of random variables is independent and identically distributed. That means each random variable has the same probability distribution as the others and all are mutually independent. Last, as is stated, we assume that xi follows a normal probability distribution. Actually, those three assumptions can be relaxed. We will talk about it in the last of this video clip. Anyway, the beauty of the model is that the distribution is parameterized by each mean and standard deviation, and so those two parameters characterizes the process. Note that xi is a random variable, so its value changes constantly, but we assume that the underlying distribution it follows may not be changing. This underlying distribution characterizes the process and regulates the behavior of x being observed. It means we can just check the state of process by observing or monitoring those parameters. Actually, we can define two states of a process: in control state and out of control state. We say a process is in control when mu equal to mu 0 and sigma equal to sigma 0, where mu 0 and sigma 0 are the target mean and target variability associated with the process. In control state is statistically stable state where only random cause of a variation present. On the other hand, a process is out of control when mu is not equal to mu 0 or sigma is not equal to sigma 0. This is statistically unstable state. When the process is out of control, we say assignable causes are present, and these causes are responsible for the process changes. For example, this figure shows many potential abnormal scenarios under normality assumptions. There could be an assignable cause which increases the level of outcomes, increases the variability of outcomes, or both. To figure out what current state of process is, we need to know the mu and sigma. The question is how to know mu and sigma. We need a statistical tool called parameter estimation. The parameter estimation enables us to find out the value of parameters of the selected distribution using collected data from a process. In the parameter estimation theory, it is known that sample mean and sample variance are good estimators of mu and sigma, respectively. In practice, instead of sample variance, sample range is also very popular estimator of sigma. And therefore, we can calculate sample mean and sample variance from observations. If they are similar to target mean and target variance, we classify the process as in control state, while if they are quite different from them, we classify the process as out of control state. Then how to decide the value is similar to or different from target values? Here, we need another statistical tool called the hypothesis testing. I'm not going to talk about the details of hypothesis testing in this time, but using the tool, we can make a decision whether a sample statistically indicates null hypothesis, which means the in control state, or alternative hypothesis, which means out of control state. This sample by sample hypothesis test is called control chart, which is the basis of abnormal detection or real-time monitoring system. Control charts are a very popular statistical method to detect a change in the process or the underlying distribution. So far, we have discussed the concept of control chart, which is one of the main statistical methods for quality improvement. In the way to explain the concept, we have talked about variance, data, and some statistical tools under simplifying assumptions such as univariate data type, IID, and normality. Of course, we may need to consider more complicated but realistic settings by relaxing those assumptions. This is very important because today, the shape of data becomes complex as process gets complicated. For example, advanced manufacturing process such as 3D printing, additive manufacturing, micro-manufacturing accelerates the complexity of problems and requires more advanced statistical methods. As introduced in the beginning of this time, the simplest model would be only one random variable for a single quality characteristic under IID and normality assumptions. It is a natural extension to consider more than one variable for multiple quality characteristics. Moreover, sometimes output variable of interest is associated with other variables, that is a function of another variable. We call it profile data. Profile data can be extended to more complicated surface form as shown in the figure. Besides the complexity of the data shape, IID assumption can be relaxed, and we may consider correlation among observations. In terms of model, instead of a normality assumption, we can develop various types of probability distribution, or even distribution-free approaches can be considered. In this time, we discussed the basic concept of statistical model for process improvement, 3 underlying assumptions, and their extensions. Thank you.